Well, hello everybody. In this video, we're going to talk about the last topic of chapter 2, atomic spectroscopy. Well, this is one of the slides from the first topic, okay, the nature of light. And in this slide, we briefly discussed how the atomic spectroscopy of hydrogen looks like and why we got these lines, okay, for hydrogen atomic spectroscopy. Well, we said that when the electrons move from high energy level to low energy level, then this process will release a photon, and then these photons are in the visible light range, and that is why we see these different lines. Okay, of course, different lines represent the transition of the electrons from different energy to low energy level. Okay, but the question is, how does this start from the very beginning? Okay, um, so let's take a look at this picture, and I believe it will give you better ideas about why we see these lines from the very beginning. Well, first thing is, in nature, every thing will find its most stable form. Okay, that's generally true. Um, well, for hydrogen atom, the electron will be on n equals to 1 level. Remember when we discussed the 4 quantum numbers, okay, in topic number 2, we did the calculation, or I showed you the energy levels for the different n values, right? The n equals to 1, the energy is the lowest one, so it's the most stable um, orbital. Okay, so when n equals to 1, it's the most stable energy level, and in nature the electron will be on this level. But if you use some methods to excite this electron to high energy level, for instance ionization, okay, you can burn it, you can provide heat energy, or you can use some strong light beams to shoot these electrons and let them jump to high energy level. Okay, now when those electrons are on the high energy level, they are not going to be stable. Okay, they want to go back to the low energy level and to become more stable. And when they go from high energy level to low energy level, they are going to release energy. It's sort of like you drop a weight from the fourth floor to the first floor. The fourth floor, you have higher potential energy, right? Once you drop the weight, the potential energy will be converted to kinetic energy, and so the weight will the speed of the weight will become faster and faster due to the gravity. And here it's the same thing. When you have electron at the high energy level, okay, when they go back to the low energy level, that energy difference will be released by as a form of light. Okay, so that's the basic mechanism. Now, in this picture, you can see that when the electrons go from n equals to 5 to n equals to 1, or n equals to 4 to 1, 3 to 1, 2 to 1, okay, these electron transition process will release photons, okay, in the ultraviolet wavelength range. In other words, those photons, okay, will be the ultraviolet light, and our eyes cannot see those ultraviolet lights. Okay, so we cannot see them by our eyes, or cannot observe them by our eyes. Okay, but we have to use the special instrument if we really want to see them. If those electrons go from n equals to 5 to n equals to 3, or n equals to 4 to n equals to 3, they will also release photons, but the energy of those photons are quite small, so the corresponding photons released by those electron transitions, okay, will be quite small. So they are in the infrared light range. Again, our eyes cannot see these infrared lights, So we will have to use this special instrument to see it. Okay. All right. But if those electrons go from n equals to 5 to n equals to 2, n equals to 4 to n equals to 2, n equals to 3 to n equals to 2, the, the photons released by this electron transition process, okay, can be observed by our eyes because the wavelength of those photons will be in the visible light range. Okay, and of course they will have different colors, okay, because they have different wavelengths. All right, so I hope this picture tells us the basic mechanism of the atomic spectroscopy. You have to excite the electrons from low energy level to high energy level. And when those electrons go back from high energy level to lower energy level, they will release those energy in the form of photons. Okay? All right, so one question remains would be, how do we calculate the wavelength of those photons? Well, we have equations for us to use. Let's use this example to demonstrate. Okay, so first you excite the electron from n equals to 1 to n equals to 3, and this electron will go back from n equals to 3 to n equals to 2, and meanwhile release the energy in the form of light. Okay, so what do how should we calculate the wavelength or frequency from of those photons? Well, one equation can help us. Okay, and that is a Redberg-Balmer equation. Let me write it here. Okay, let me use the red color. Okay, here is the equation. 1 over lambda equals to R times 1 over NF square minus 1 over NI square, parenthesis. Okay, let me explain it a little bit. Lambda, of course, we know it's wavelength. Okay, how about R? Well, R is a constant, Rydberg constant, that is 1.1 times 10 to the 7 meter to negative 1. Okay, sometimes you can see textbook using 1.097 times 10 to the 7 meter to negative 1. Okay, it doesn't matter which one you prefer. In this video, we're going to use this value. We don't need to pay attention to the significant figures of those constants anyway. Okay, so it doesn't matter. Now for NF, okay, that's the final principal quantum number of the electron transition. For instance, if you have electron going from n equals to 3, n equals to 2, that means NF would be 2, the final principal quantum number. And accordingly, okay, let me write it here. Ni, that's going to be initial n. Okay, in this case, Ni equals to 3. Okay, so this equation is quite simple, and I believe it can help us calculate the wavelength very quickly. In your textbook, they used a different equation, and let me write it here. Okay, so delta E equals to negative E electron equals to 2.18 times 10 to the negative 18 joule 1 over Ni, 1 over Nf square minus 1 over Ni square. Okay, and then delta E equals to negative delta EP, and then you can calculate the energy of the photon. I personally think this process is a little bit too much and too complicated for us. Redberg equation essentially includes both of them. Okay, so I think this one, Redberg-Balmer equation, is easier for us to use. And this equation, this constants, will be given in your test. Okay, so you don't need to memorize this equation or constant. You just need to know how to use it. All right. Now, as I mentioned that for this particular example, the electron goes from n equals to 3 to n equals to 2. So let's just use this example to calculate what the wavelength of this photon is. Okay, so let's just plug in a number and then find out. Step 1, I'll write it here. Okay, so step 1 over lambda equals to 1.1 times 10 to the 7 meter to negative 1. According to our analysis a moment ago, goes from 3 to 2. That means NF would be 2. Okay, so it should be 1 over 2 squared. Okay, now Ni would be 3 because that's the initial N value. So 1 over 3 squared. Okay, we need to be careful when you set up the equation. Now the rest of it would be just do the calculation step by step. Okay, so that tells us 1 over lambda equals to 1.1 times 10 to the 7th meter to negative 1. And the part inside the parenthesis, my calculation tells me it's going to be 0.13889. Okay. Again, don't worry about the significant figures because these 2, 3, they are constant. Okay. All right. Now the next thing is going to be about this part. Okay. Now this part, if you multiply them together, 1 over lambda, that will give you 1.5278 times 10 to the 6 meter to negative 1. Okay. Well, if this number, this is the intermediate answer. So in theory, we should follow the significant figures from these two numbers. However, as I mentioned, that this constant, this Redberg constant, right? So in this particular calculation, essentially, you don't need to pay attention to the significant figures. Okay. Now, what's next? Well, according to my experience, a lot of students will get confused about how you solve lambda when you got here. Well, let's do this step by step. Okay, well, lambda is at the bottom, so how do you flip that on top? Well, the thing is, you can multiply lambda on two sides. So you multiply. Let me write that with the red color. So you multiply lambda on two sides. Okay, so you can cross the lambda. So that is how we flip lambda to the top part. Okay, so on your left side, it would be 1, and that equals to 1.5278 times 10 to the 6 meter to negative 1 times lambda. And then how do you calculate lambda? You divide the two sides by this number and you got your lambda. Okay, so lambda equals to 1 divided by 1.5278 times 10 to the 6 meter to negative 1. Okay, and my calculation tells me that's going to be 6.5 times 10 to the negative 7 meter. Okay, Well, if the question is asking you to calculate the lambda only, then you can just stop here, okay? But as I mentioned in our first video, for most calculation involving wavelength, we are going to use nanometer for the units of the wavelength. Okay, so let's do some extra step. Convert this meter to nanometer. All right, so step 2, 6.5. All right, one thing, the reason why I want to keep this as a two significant figures is no reason. Okay, so you can keep that as a 3 or 4, 5. It doesn't matter because in this particular calculation, constants, all of the the digits or numbers are constant. So significant figures is not that important in this case. Anyway, let's continue. Times 10 to the negative 7 meter. Okay, so this is going to be a very simple unit conversion. Okay, so we want to cancel meter, so the meter should be at the bottom, nanometer should be on top. Okay, we know that 1 nanometer equals to 10 to the negative 9 meter. Okay, let me write this better. Okay, negative 9. All right, so if you do the calculation, and that will give you 6.5 times 10 to the second nanometer. Okay, so this is our calculation. Of course, if you want to do one more step, why don't we just go ahead and do the practice here. Okay, so we got the answer as nanometer for wavelength. What if question asks you to calculate the frequency of this photon? Well, you just need to do one more step. Okay, so number 3, step 3, use the nu equals to c over lambda. Let me use different colors so you can see it better. Okay, so well, c, speed of light, 3.00 times 10 to the 8 meter per second. Okay, divided by lambda, and you have lambda. Well, in this case, it might be better for us to use this value because this value is the meter as a unit, and we need a meter here. So let's just use the meter in for lambda. 6.5 times 10 to the negative 7 meter. Okay, and if you do the calculation, that will give you 4.6 times 10 to the 14th 1 over second, or hertz. Okay, so here, I hope this example demonstrates how we use Redberg-Balmer equation to calculate the wavelength lambda and the frequency of the photons emitted by the electron transitions from n equals to 3 to n equals to 2. And we will do some other practice when you come to class. Okay, so but if you have any questions, please tell me.